Once you've described the load on your system using load parameters, you can investigate what actually happens when load increases. The book frames this as two distinct questions. First, if you increase a load parameter while keeping system resources, CPU, memory, bandwidth unchanged, how is performance affected? Second, if you increase a load parameter, how much do you need to increase resources to keep performance the same? Both questions require numbers. So what numbers do you use to describe performance? The answer depends on what kind of system you're building. In batch processing systems, Hadoop, for example, you usually care about throughput, how many records can you process per second? Or equivalently, how long does it take to run a job on a dataset of a certain size? In online systems, APIs, web services, databases, what matters is response time, the time between a client sending a request and receiving a response. Now, the book makes a distinction that's easy to miss. Latency and response time are not the same thing. Response time is what the client actually experiences. It includes the actual service time, plus network delays getting there and back, plus time spent waiting in a queue. Latency is narrower, it refers specifically to how long a request is waiting to be handled, before processing even begins. When you report performance numbers to stakeholders, you almost always mean response time, not pure latency. Keep that distinction clear. Here's something fundamental. Even if you make the exact same request to the same server over and over, you will get a slightly different response time every single time. This is not a bug or a mystery, it's the nature of shared systems. A context switch to a background process might add a few milliseconds. A garbage collection pause might add tens of milliseconds. A network packet getting lost and requiring TCP retransmission can add significant delay. A page fault that forces a disk read. Even mechanical vibrations in the server rack have been measured to affect disk latency. These sources of variation are always present. So the book makes a critical point: stop thinking of response time as a single number. Think of it as a distribution of values that you can measure. Imagine a bar chart where each bar represents one request, and the height of the bar is how long that request took. Most bars will be short, most requests are fast. But occasionally you'll see a bar that's much taller, a slow outlier. Now, the most common way to summarize a distribution is the mean, the average. But the mean is a terrible metric for response time. If 95% of your requests take 10 milliseconds and 5% take 5 seconds, your mean might be something like 260 milliseconds, which sounds fine and tells you almost nothing about the 5% of users who just waited 5 full seconds. The mean doesn't tell you how many users actually experienced that bad delay. The right approach is percentiles. Here's how to think about them. Take all your response times and sort them from fastest to slowest. The median, also called the 50th percentile, or P50, is the value at the halfway point. Half of requests are faster than the median, half are slower. If your median is 200 milliseconds, that means half your users got a response in under 200 milliseconds. The median is a much more honest metric than the mean because it directly corresponds to a real user experience. But the median only tells you about the middle. What about the slow end? For that you look at higher percentiles. P95 means 95% of requests are faster than this value, and only 5% are slower. P99 means only 1% are slower. P999 means only 0.1%, 1 in 1,000, are slower. These high percentiles are called tail latencies. And they matter more than most engineers realize. Amazon tracks P999, the 99.9th percentile, for its internal services. Why would you optimize for such a tiny fraction of requests? Because the customers whose requests are slowest are often the ones with the most data in their accounts, they've made the most purchases, they have the most history. They are, quite literally, Amazon's most valuable customers. Amazon has measured directly that a 100 millisecond increase in response time reduces sales by 1%. A 1-second slowdown reduces a key customer satisfaction metric by 16%. These are not theoretical concerns. They are measured business impacts. That said, there are limits. Optimizing the 99.99th percentile was deemed too expensive for Amazon's purposes. Response times at very high percentiles are easily affected by random events completely outside your control, and the benefits diminish as you push further into the tail. There's a rational trade-off to be made. The book's recommendation: use percentiles in your service level objectives and service level agreements. An SLA might say, median response time below 200 milliseconds, P99 below 1 second, service available 99.9% of the time. This sets contractual expectations for clients. If the SLA is not met, clients can demand refunds. These aren't just internal targets, they're commitments with consequences. There are two more important concepts the book covers. First, head-of-line blocking. A server can only process a small number of requests in parallel, limited by CPU cores. So requests queue up. If even a small number of slow requests get to the front of the queue, every request behind them has to wait, not because those later requests are slow to process, but because the slow ones are in the way. The client sees the total waiting time, including time in queue. This effect means that high percentile response times are strongly influenced by queuing, not just processing speed. This is why the book insists, measure response times on the client side, not the server side. The server might think it processed a request in 10 milliseconds. But the client waited 500 milliseconds because it was sitting in a queue behind a slow request for 490 milliseconds. Second, tail latency amplification. This is subtle and important. In modern systems, a single user request often triggers multiple backend calls to a database, a cache, a recommendation service, and authentication service. Even if each of those calls only has a 1% chance of being slow, when you fan out to 7 backend services, the chance that at least one of them is slow becomes much higher. And the user's request isn't done until the slowest one finishes. This means a small percentage of slow backend calls translates to a much larger percentage of slow end-user requests. Google researchers named this tail latency amplification. One practical implication, calculating percentiles correctly is non-trivial. The naive approach, keep a list of all response times and sort every minute, is too expensive at scale. More efficient algorithms exist. Forward decay, T-digest, and HDR histogram can compute accurate approximations at minimal CPU cost. One important warning from the book, averaging percentiles across machines or time windows is mathematically meaningless. The correct way to aggregate percentile data is to add the histograms together first, then compute percentiles from the combined histogram.